Hi student, and in lecture 7 we are discussing new topic or the next sequential topic of previous analysis. In the previous lecture we discussed the small signal model of flyback converter, offline flyback converter with optocoupler isolated P color mode control. Okay, so now we start discussing the control of offline flyback converter. So first, I present the current loop design. We define the current loop and the voltage loop. So there are two designs. One is current loop design and the voltage loop design. Once we finish the current loop design, we can evaluate the control to output transfer function with current loop closed. I'll explain that later in detail. Then remaining step is just the voltage loop design. So there are three different tasks here. Okay, I won't write down here. Okay, but during this lecture, that concept will become evident to you. Okay, let me show you this. Right, there is the schematic of our converter, our offline converter. So this component with the black line is already fixed. This is determined by the IC designer, this voltage, then this height of the lamp, and the period of lamp is fixed, okay? And this RB is fixed for the biasing of this is not related with this dynamic analysis and the design, okay? Because the own resistance of this is small, this is relatively large, can be ignored, okay, because the parallel combination of two different values of resistance, okay, you can kick out the larger one. And this one is used to control this out voltage. So only these 4 components are related with voltage loop design, okay, and only these two components are related with current loop design. Okay. In the previous lecture slide, so there is a clear distinction between VI and V lamp, but somehow this is the mixed. This lamp, original lamp is generated here, then that lamp is going like this, and voltage division is coming here. So this voltage is this one. V com is the reflected lamp. V lamp prime plus IQ RI. So this is the effective current sensing network. This is different from this because of this structure. Okay. So later on, I'll show the simulation result of this. That waveform is different from our conceptual this diagram, because two signals are not completely separated. VI and this lamp signal is somehow mixed here. So two mixed signals will appear here. Okay. Important thing is current loop design. We should determine this V lamp prime. This is the V lamp, and the V lamp will be divided by these three resistance and appear here as V lamp prime. So we should find this V lamp, or we should design this V lamp, and RI is current sensing network gain. There are three resistance associated with that. So IQ switch current is coming down here. This is IQ. IQ is coming down here. But during this small signal analysis, this should be grounded. I'm talking about the superposition. Then that current will be divided into two paths. But this is much smaller than this. So all the current will go like this. Then this is the VI, but this VI is divided by this one and this one because this is grounded. Assume this is 0.1 ohm. Then this is the same. Then the RI is 0.1 divided by 2, 0.05. Okay, there are 6 dB difference between this value and actual. this current sensing network gain Ri. Okay, so you should consider this, and this is the only equations we're going to use to determine value of this. Okay, first we determine from the theoretical work, we determine the required this one. Then for the circuit implementation, we determine this and this. Okay, because there are two equations and the two unknowns is solved easily. Okay, that's it. That's about this. And this structure, I said this structure is this two-pole 1-0 structure. So we have integration structure. So DC regulation is guaranteed, and the KB is this times this. Okay, very long. This quantity multiplied with this is the KB, and this pole frequency is this one. This is zero frequency. So zero frequency is you can not arbitrarily. You can freely select this, but the other thing is already determined because this R1, R2, and RP are determined by this IC designer, and this omega PC, this is determined, okay, by somebody else, and CTR is determined by this optocoupler people, okay, and the CJ, minimum value of CJ is fixed by this device. You can increase this by adding some additional capacitor in parallel, but this minimum is bounded. So minimum, this CJ is bounded. As I said, Vm prime here, seen by here, is bounded. Maximum value is bounded. Okay, this must be smaller than this. Okay, so you ground here, no, you cut here, then you will get this. But eventually, this Vm prime magnitude of that should be smaller than this. Okay, that means the compensation ramp slope is smaller than maximum of this one. Okay, so it's very easy. Just determine these two and these three. But we determine very systematically, okay, theoretically. So first one is current loop design. So let me go through this slide. Okay, then we stop here. This is small signal block diagram of our system. Okay, we're not going to use this circuit model. This circuit model is sometimes circuit model is not shown here in the previous lecture slide. Circuit model is sometimes good when you are deriving the transfer function of something. If transfer function is they are already derived, then this is the best. Okay, so that's the reason why the control people is using this block diagram all the time. Okay, we do the same thing. Okay, so first one is current loop design. So you are trying to shape this structure of the structure shape of this TI. Okay, so TI, this one, multiplication of three transfer functions. This one. We are only considering this current path. Okay, so TIS is this one times this one times this one. So this one is this one. Okay, so it is quadratic function, the DC gain, and this 0 and double 4. This is constant, and this FM prime is also constant. Okay, and you combine all together. So you combine all constant here. This is a constant, this is a constant, this is a constant. Okay, this is not frequency dependent term. That is Ki. Okay, so Ki is actually this one. This one is FM prime. This one is FM prime. And all of them, combined all of them, is this one. I wrote down here. KID is this one. Low frequency gain of duty ratio to current transfer function. Then just take a look at this. Okay. So this is the low frequency asymptote, and this omega ID is coming first. So increase is, the slope is increased by 1. That means it becomes +1 slope, which means 20 dB increase per decade. Then you have double pole here. Then this +1 slope becomes -2, which means -20 dB per decade slope. So this is the structure. Okay. Think about this. This is the Ki. Okay. So if Ri is fixed, this will be fixed because the input voltage and output voltage are fixed. Then this one is fixed. Then you can play with this one. Maybe you may select, you may play with this one. Okay, you can increase this. You can increase this with small slope. This one with large slope. This one. Okay, large slope with this one. Then it increase. Then the asymptote will move down. It sinks down. Okay, because this becomes small. Then Ki, this becomes large. This becomes small. Then this one sinks down. So it start from here and start from here, start from here. Okay. For some case, people want to increase the SE. Okay. Something bigger is good, which is not true here. Okay. They increase this. This is so large. Then this will be much larger than this. This will be gone. Then only this one remains. That means what? Voltage mode control. Okay. The feature of the current feedback is reduced. Only remaining part is this. If it becomes below this one, it entirely sinks down. Then all of the feature, you have the shape and structure, circuit component of current mode control, but you are doing it just the same as the voltage mode control. Okay, so the reduced benefit of current feedback. Current feedback will be gone to increase this. Okay, so selecting this one is the only design option. Okay, there are many things, but everything is already fixed. There is a standard procedure of developing this. Okay, and one step of some interest of some academic value is selection of this. Whatever you do in current mode control, the only one you can play with is selecting this. Okay, right. So this one is fixed. So you want to change this, then Ki is, you can change this. This is fixed. Everything is fixed except this one and this one. This is also fixed. If Ri is fixed, this is also fixed. Okay. So for the given condition, given power stage parameters, you should select Ri and Fm prime, and Fm prime is this SN, SF select. So the only means of changing this is you are changing this. Then that is the same as changing this V lamp. Okay, then is just changing this. There is only one choice of this. Okay, then Ri and Fm prime, namely V lamp prime, should be selected for the desired TI structure. So desired TI structure is fixed actually. It has this 0 here, double pole here. What I mean the structure is this frequency. This is the 0 dB frequency of this TI as omega CI. Selecting omega CI is the only free variable in this current mode control. Okay, very simple actually. You place this here. They changes value of your compensation lamp slope. That changes value of this one. Okay, so we'll go through all the details of selecting this. Once this is selected, and you evaluate control to output transfer function with current loop closed. So this is determined. Then you evaluate transfer function from here to there. Okay. Then with that information, you design this FBS. That is the voltage loop design. First one is current loop design. Then second one is derive transfer function from here to there with this loop closed. And final step is you design this for the obtain the stability and the desired closed loop, dynamic performance, closed loop, frequency domain, and the time domain performance of your converter. Okay. This video is cut in the middle because of the prefixed class hour. So this is the direct continuation of previous lecture, and the former part is covered in the previous lecture slide, right? So, but I made one minor changes. Title of this lecture is slightly modified. Previously, the lecture title is Control Design of Offline Flyback Converter, and I divided this lecture into two parts. One is lecture 7 and the other one is lecture 8. Okay, because the topic can be long, so I divided into two lectures, and this lecture will cover current loop design and control to output transfer function evaluation with current loop closed. Okay, and the next coming lecture will cover the voltage loop control design and the evaluation of closed loop performance of this converter. We went through this already, 3 pages. Okay, so this is the new slide. And another thing is, I think I forgot to mention this in the previous lecture. Whenever we are talking about the current loop, voltage loop, or loop gain, you are putting this minus sign in front of that, in front of this definition. So you are putting this minus sign in front, then this current loop Ti is this times, this times, this times, and there is one minus sign here, which indicates the negative feedback nature of our control. Okay, so by putting minus sign in front of this, we avoid to deal with the negative something. Okay, dealing with the positive thing is much easier than the other way around. Okay, and we went through this. This is the asymptotic plot of current loop, which is the product of 3 transfer functions, GIDS and RI is current sensing network gain reflected from the primary side to the secondary side. So we multiplied, we have factor N here, and FM prime is the modulator gain of peak current mode control, and this DC term, this is a constant term, KID is constant, and this is the constant, this is constant. They are merged into this one constant KI. Okay, so KI is this one, and the KID is this expression. You can derive this from the power stage model, and let me denote this as the equation number 1. We'll be using this equation later. So this is equation number 1. So number 1 is here. Okay. So this is the directly derived from the expression of TIS. Okay. And we'll derive another expression for this KI, this KI number 1 is derived from the transfer function directly, and we have another expression for KI is derived from this asymptotic plot. Obviously, this value is 20 log KI, this one, and we have omega ID. So this slope goes up with +1 slope, and at this omega naught, you have double pole. So +1 slope changed to -1 slope, and it's declining, and this is the omega CI is loop gain, 0 dB, loop gain crossover frequency. Okay? Then start from here. So this is log scale. So we have multiplication. Then we are adding things in log scale. So this plus from here to there, slope is 20 log something. And from here to there, slope is minus 20 dB per decade. Then you swap the numerator and the denominator. This is negative sign. Okay. Then if you swap this numerator and the denominator, then you convert these things into linear equation. So this is the linear equation. Okay. So if you decide omega Ci current loop crossover frequency, the corresponding value of Ki is simply determined by this equation. This is the same equation. Okay. This indicates the theme of current loop design is to select omega Ci at the desired frequency. Usually, this omega Ci will locate between 0.1 to 0.3. Omega S is the switching frequency of your converter. So this is the general rule. So you select omega Ci first, then you have this equation, and you have this equation. This is the second equation. So denote this as equation number 2. Okay. So we have basic equation to design the current loop of this converter. So this is the expression of the Ti. Ki is this one. This was the equation number 1. So okay, this was green one. No, green one. Dark green color. Number 1, and second one is number 2 was in red. And you have another equation coming from definition of this modulator, gain of P current mode control. So this is number 3. So we have 3 equations. Okay. First, Ti crossover frequency, somewhere here. Okay. So omega S is the switching frequency of this converter. Then if you select omega Ci, then compute this. This is the using this equation number 2, right? So this is the from equation number 2. Okay, so Ki, you calculate Ki first. Then determine this. This Ri is current sensing network gain. Okay, and the Vmax is the maximum voltage which the PWM chip can handle. Okay, then maximum is determined by this IC chip, but somewhere 1 or 2, something in between. Okay, so this IL peak, because we are sensing switch current, which is the on-time inductor current. So maximum value of this current times current sensing network gain should be smaller than omega max. V max. Okay. So considering this, you select somewhat arbitrarily Ri. Okay. So keep this in mind. If this is 1, you select 0.7, 0.8 might be okay, but 0.9 will be dangerous. Okay. Then this Ri is selected. Okay. Then we have another expression of this number 1. Then calculate this. Okay. This Ki is fixed, determined here. Then you can calculate Fm prime using this equation number 1. So equation number 1 is coming here. Then you find out, you compute this Fm prime, and the equation number 3 is coming here. From equation number 3, you calculate the desired slope to have the desired Fm prime. Okay, then everything is determined. Then finally, you have this information, SE, slope of compensation lamp is known, and the switching frequency is known. Then calculate this Vi prime. So final result of this design is actually this one, this Ri value. Where is Ri? Ri, and this Vlamp is final result. Okay. So next task is determine Rcom and Rsense for the desired value of Ri. Evaluate at this number 3 and Vlamp prime to obtain this, and you select these two values. Okay, that is the step of determining two values of two resistance, which is fairly straightforward. So we have example here. Okay. So this design is done at this point. This is the wrong point. Somehow I select this. Okay, but we should select the minimum input voltage, which is 110, and we should select the maximum current, which is 10 amp. Okay, this is not the worst operating point. Probably this will be the best operating point, but somehow in the long time ago, I used this. Okay, but really very conservative. So phase margin will be, if phase margin is something similar to 60 degree, this design might be okay. I checked this out. This design is all good for, we have 4 corners because the line load, heavy load, low line, high line. So this is okay. Okay, but this is not the best choice. If you select your design this again, you should select this VS of 1 something, the low one and the highest value of this. Okay, so this is not a good selection. Okay, I know this, but I decided to use this data here. Okay, probably you will have 2 chances to redesign everything at the desired operating point. Okay, worst case operating point. All right, probably you will have a chance of doing that. Anyway, for this case, this is the input. Input is this one, 310. Okay, 310 volt, and output. This is always regulated at 10 volt by fixing this. This is the 2.5. Then this is some number 770 ohm, something like that. So our voltage is always regulated at this point. Then this is the voltage gain expression of flyback converter. D comes from the buck converter. 1 divided by 1 minus D comes from the boost converter. And this number is coming from the turns ratio. So D is 1/4. And this is the GID expression. You calculate this. Okay. And omega ID is the 0 in the numerator. And omega ID you calculate. Then IQ max, you should know this to determine what? Ri. Okay. So this part is IO, and n times this, and this is the IM, average value of load current and average value of the magnetizing current. Okay, this entire thing is average value of magnetizing current, and this is the del IM, variation of IM, excursion of IM, and this plus half of this is the peak value of IQ switch current. Okay, so you evaluate this. So this is 1.5 amp. Okay. And this value, R lamp, this is R lamp, and RT and R1, R2 are all determined by the IC designer, and V lamp is fixed as peak value of V lamp is fixed at 2.3 volt. So with this, we control this to have the desired value of Ri of 0.5, Ri of 0.5. Oh, it's not here, no? Okay. Right, so it's coming here. Okay. Current loop design step 1. So TI crossover frequency is selected as 0.3 omega s. Maybe this is the one challenging design. So this is okay. So I designed optimally using this number. Okay, so we select this, but you can select slightly lower than this. It really doesn't matter. Then using the equation, Ki is determined as 1.93, and the CS gain Ri is the maximum value of voltage allowable at the input port of IC chip is 1 volt, and the IL peak was 1.05. So this number is this one. Okay, Ri should be smaller than, sufficiently smaller than this number. So I selected 0.5. Okay, and the modulate again, we have another expression for the Ki, which is derived from the block diagram representation. Then this Fm prime is this number. Then if you know this number, you can calculate SE using the modulator gain formula of current mode control. Then SE is determined by this number, and the slope of effective lamp magnitude is, which is denoted as V lamp prime, is this slope times, this is what, switching period, which is 0.6 volt. Okay, so we obtained the two critical numbers here. Ri is this one, and this V lamp is this one. Okay, and the remaining step is select Rcom and Rsense to get this number and this number. With this assumption, this is obvious. This Rsense is very small, otherwise you will suffer from the excessive ohmic loss. Okay, to avoid that, it's sufficiently small, very small, 0.5 something. Okay, and this is the some tens of kilo ohms usually. So next is this one. I repeat this step number 7 here. So selection of Rcom. I don't know what is Rcom. R compensation or something. Rcom and Rsense. Rsense is a sensing resistor. Assuming this is the obvious. Okay, and this is the parameters and the circuit diagram. This is the current feedback waveforms. This part is V lamp prime. So V lamp prime is this part. It's coming here and it's coming here like this, periodic. Okay, so it's the part of partial copy of V lamp. Okay, that is V lamp prime, and this part is IQRI. This is the sensed current signal, current feedback signal, and some of this and this is Vcom. So when Vcom hit this Vcon, con is control voltage, and this value should be smaller than this. Okay, because this is the maximum voltage determined by this controller. Let me use this Vmax. Okay, Vmax is easy. All right. So this length is the same as this one, and this length, this part is this one. So IQ times Ri is this one, and this is coming from the V lamp prime is added. That becomes combination of this and this becomes this Vcom. When this Vcom intersect with Vcon, switch off signal is generated. Okay, so this is the waveform of this PWM scheme, right? And the V lamp prime, this is the V lamp, and V lamp prime is somewhere here. V lamp prime is this part. This is partially V lamp prime. Okay, so V lamp is divided by this one. Okay, and this is the division, but this Rsense is very small. You ignore this, then you have this, and this value is determined as 0.6, and this is given by this IC. Then this Rcom should be 6.4 kilo ohm. Okay, second one is Ri. Okay, desired value of Ri was 0.5. So 0.5 is current sensing network gain. So IQ is coming down from the switch. So this is the IQ. Some of the IQ is going this way. Assume this is grounded. I'm talking about the superposition. So some of IQ is going here, and some of IQ is going here. That current division ratio is this one, okay? And that current is multiplied by this R sense. That this becomes voltage. Then this voltage is divided by this 3. 1, 2, 3 resistance. That is this one. This one, no. This and this, okay? So this voltage divided by this and this. So this is current division, and this is the voltage division, and they cancel, and R sense is very small, it can be ignored. Then remaining is this, okay? This desired value of Ri was 0.5, and this R sense is determined from the equation. So R sense is 0.67. So you finish the design. This is the desired or final value of R sense and R com. Okay? Very straightforward. Okay? This is just the ohmic laws. Okay? Application of the ohmic laws. And you should design two optocoupler parameters. That one is the CTR, current transfer ratio, and the other one is this CJ, junction capacitance, between this collector and the emitter terminals of phototransistor. And to determine that, you should know two things. One is this one, DC voltage across collector and emitter of phototransistor, and the other one is IT, is the current, DC current through the phototransistor. So if you know this information, then we went through the graph determining this, then you will determine ID and the CTR altogether, and you need this, determine this is something else from the simulation or measurement of frequency response, okay, 3 dB frequency. Then you can evaluate this, but first you should calculate this, you should compute this, okay. Then this value is V con is related with this one. So V con is at this point, V con is same as V con. So if you know the V con, then you know this current, then you know this voltage, then you know everything. Okay. So V con is D times V ramp prime part. This is part 1, and part 2 is Ri, current sensing network gain, times this switch current, peak value of switch current. So this V con is 0.68. Okay. So V con is this current is 0. This is this kind of ideal OPM. So I is 0. There's no current going into it. So if you know this voltage, then you know this voltage. Okay. So from this, assume this VC, then voltage division is this one. Then you determine this. Then if you know the value of this, you know this current, and from this current, this one, you subtract this current, this voltage known, you know this, then this two current is known, then you automatically determine IT. Okay, so VCE is decided and IT is computed. Then you use this data sheet to calculate this and ID. Okay, then you calculate this IT, then you measure the frequency response of this one. Okay, we went through that, some experimental setup. Then CJ is measured. So this is the experimental value we measured long time ago. So this is the empirical data. The CTR is this one, and parasitic capacitance of this device was, this particular device was 1.3 nanofarad. Okay, so that is, now everything is known. Okay, then this is the PSIM program. So this is PSIM. So this, we determined this, and everything is known, and this is 1.3 nanofarad, okay, 1.3 nanofarad, and CTR was 0.316, is that correct? Right. Okay. So later on, we will determine this through the voltage design process. So this is the final result of our design, and this is required to provide the additional current to this OTA, operational transconductance amplifier. So we'll be using this to simulate our offline converter. So this is the result. Okay. So I provide all the PSIM files. In the beginning of this semester, you have this file. Then this file is customed to generate this. Okay. So this VCOM is IQ times RI plus D is duty ratio, and V then prime is deflect the lamp voltage. You calculate this, then this voltage is 0.68, which is the same as our previous result. Okay. All right. This part is D then prime, D times V then prime. Okay. I think I made a mistake somewhere here. So this part is this one, and the part of this blue curve is this will be same as this one because they are added, and only this part, this blue part here. Where is blue? Blue is here. Only this blue part is this one. Okay. So this plus this, okay, it should go down onto the bottom. This plus red one becomes this one, this equation, right? So everything is okay, okay? So we know this, the design of current loop is done, and it is done properly. Okay, then next step is to compute the control to output transfer function with current loop closed. This is very important. This is the basis of designing the voltage feedback circuit. So you should evaluate this, and we have this block diagram representation of this our offline flyback converter, which employs peak current mode control. This control is called two-loop control or multi-loop control because there is one loop. This is called TI, and there is another loop TB. Okay, so originally it was connected with some voltage feedback compensation, but we take that out, and you are looking this through circuit through this opening. So you are looking at this inside of this at this point. Okay, then this is the input and this is the output. Okay, so this is the transfer function of control to output variables. So this is the input variable and this out variable. This is the control to output transfer function with current loop closed. The current loop is closed. You apply the Mason's gainer here, or you use the simple this block diagram manipulation, then result is this one. Okay. Whenever you have this feedback structure, denominator is 1 plus something, and this is the open loop transfer function, which is this times this. Okay. So you have this, right? So this is the previous current loop. So this is the reason why we first designed the current loop. Once current loop is designed, then you can evaluate this. Okay. If you know this transfer function, it's very easy, very straightforward to design the voltage feedback compensation properly. Right? So this is the procedure, and again, we have this negative sign indicating the negative feedback. Then, because of this, we add another negative sign in front to avoid to dealing with something negative. Okay, so this definition, or simply you multiply this and this without paying any attention on this, then that's okay. All right. Okay. This is the conceptual explanation about evaluating empirically. This can be done in the computational method, time domain simulation, or can be done through the experiment. So this setup is the same. The same setup can apply either the experimental work or a computational method. So this is the voltage feedback compensation part, right? And you cut here, then you add this. Then you excite this and measure this using your equipment. That is the measurement. You excite this with your simulator with the sinusoidal wave by changing, while sweeping the frequency of sinusoidal waveform. And because the sinusoidal portion of this, that is the same as the measurement, that is the computational method using time domain model. Okay, that the computational method is not analytical work, just simple simulation, numerical simulation, same as experimental measurement. Okay, so this setup, I prepared this slide to give some information about this. I showed my prototype previously, and this part was on the prototype. Okay, it was a part of that hardware. We added this part to measure something. And this is the voltage feedback circuit. All right. Okay. This is the expression of control to output transfer function with current loop closed. Okay. So you know this transfer function, this number, this transfer function, you know this. You add one and calculate this. That is the volts approach. Okay. That you cannot get anything meaningful. Right. So we use some asymptotic method. Asymptotic method is we divide the frequency of our interest into two portions. One is this part where magnitude of the Ti is larger than unity, below the 0 dB crossover frequency, below the frequency of omega Ci, using the notation you are using, that is the omega Ci. So below the omega Ci, you ignore this, and after omega Ci, where magnitude of the Ti is smaller than unity, then you ignore this, then you take this. Okay? So separate into two parts. That is called asymptotic approximation or asymptotic analysis. Okay? That is very graphical way of doing this. Okay? This is Ti. We went through this. It starts from the DC value at low frequency, and it has 1, 0, a double pole. It goes to this with -1 slope, which means -20 dB per decade. It rolls down forever. Okay, and this is the FM GVD. This is the low frequency component. This is constant. So GVD has constant in front, which is KVD times FM prime is also number. So this is the horizontal line, and at this frequency is what? This is the double pole frequency, omega naught. This is omega naught. Okay, and after that it declines with -2 slope, -40 dB per decade slope, and it hit this omega ESR 0 here. Okay, ESR 0 here, and it goes -1 slope, and finally there is omega RHP. This is 0 in terms of magnitude. So it goes in this horizontal slope of 0. So this is the GBI asymptotic construction. So this one simplifies the analysis. You don't have to calculate anything. Just graphically you sketch this. Okay. Another advantage of doing this is this asymptotic plot can be immediately transformed to the equation, factorized equation with very good accuracy. Right? So for this converter, the order of this frequency is this one. Omega ESR is coming first, and omega RHP is coming later. In between, there is omega CI. Omega CI is current loop crossover frequency. So based on this our rule, up to this point, so this is generate GBCI, magnitude of this is generate, subtracting this curve by this one. Okay. So at low frequencies, this much is subtracted from the upper curve. Okay. And at this point, at the double pole frequency, this much is subtracted from top curve. So this should be the same. Length should be the same. Okay. And you can calculate the slope here. This is zero slope, and you are subtracting this slope from here. Then there is you are subtracting this increasing slope. Then this will be declining like this, and the difference of the order is 1. Difference of this this slope is 1. Then it has same slope here. Okay. Then this slope and this slope is the same. It goes in this horizontal line, and after this frequency, it just follows. This follows just this one. Okay. So it goes like this. Okay. This is a phase curve. It starts from 0 and go to this -1 slope, means phase is dropped to -90 degree, and there is a 0 is increasing, and this omega RHP is pole in terms of phase, it goes down. Okay, so this is the prediction of these characteristics. The same thing. Okay, so I copied this and I magnified this part. All right. So this is the expression for up to this part. This omega before omega CI. This is the very good approximation, extremely accurate approximation. Before this omega CI is here. This part. So we are largely interested in below this region. So we are using this. And we evaluate the DC value of this transfer function and denote it with KVCI. Then this one is Fm prime here, and this is the DC value of this, and you cancel everything, and this is the final result. Okay, which is this. Okay, this is this magnitude of this horizontal line, and this one. And one important observation here is there is a peaking. There is a second order feature here. This is second order feature here. But this one has also second order feature. So second order feature, they are cancelled. The features are cancelled. And this is this first order characteristics with -1 slope. So this is effectively removed. Okay. Dynamics associated with power stage double pole is cancelled, so it's not showing up in the control to output transfer function with current loop closed. Which one is this? And we determine this. Okay, so here we calculate this number. Same thing. Okay, asymptotic plot of magnitude, asymptotic plot of phase, and this is a relationship between this location of omega ESR, omega CI, omega RHP, and again omega CI is current loop crossover frequency. It's extremely important to design this everything properly. Okay, so you select omega CI between 10 to 30% of switching frequency. That is fine. Okay, that is fine. Then you don't have any problem. And the equation of this is DC. So this value is the KVCI. You have this is pole is appearing here. Okay, and you have this 0 is showing up here, and you have another pole here. So there is a pole at the loop gain crossover frequency, and finally you have this RHP 0. Okay, so this equation, and this is derived graphically, and you type number here, and you compare with the prediction of this equation and the bright false simulation, computer simulation, or MATLAB prediction. You cannot tell the difference. They are almost the same. Okay, so this approach is very effective. Okay, extremely simple, and it provides many design insight. Okay, if you play with the exact equations, you will be lost very soon. You may don't know what you are doing. Okay, so we determined everything, and we want to simulate this one. Okay, this is the PSIM setup. Okay, so this is the computational method evaluating this control to output transfer function with current loop closed. Okay, so still this one is here. In previous diagram, I cut this point here, but you don't have cut here. Okay, you are using this. This is some special feature provided by PSIM. This AC is AC scope something, AC proof. Okay, then this dot is important. Dot terminal becomes denominator. Whatever connected to this terminal becomes denominator, and whatever connected to the other part, undotted part, becomes numerator. Okay, so denominator is connected to here. So denominator is connected to here. Okay, so this is what? We have this PWM modulator here. So this is the free cone head. If we only consider AC component, this is free cone head. And if we only consider AC component of our voltage, then this is what? This is VO head. This is VO head. So what you are simulating is actually GVCI defined as VO head divided by control voltage head. Okay. So this program is automatically generating transfer function from here to there with everything connected. Okay. So this is very convenient to use this AC proof or something, but you should know this. If you convert these things, you are measuring something else. Probably inverse of this or something, I don't know. Okay. Sometimes it generates the error message. Something is shorted, something like that. Okay, make sure when you are using this is going to denominator, and the other part is appearing as numerator. So this is what? This is control to output transfer function, which is this. Okay, this is very similar to the structure of two-pole one. No, not this one. This structure, right? So this flat gain and slope, and this one phase is something like this. So we confirm this is correct. So magnitude asymptote is correct, and phase is at high frequency. It goes down because the what? RHP 0. Okay. There are something more, the sampling effect of this current mode control. Then, but if you follow this guideline, you forget about the sampling effect. Okay. There is usually, most cases, some smart guy was cheating us. Okay, so forget about that. So this is called classical design approach. Is more than enough for almost all practical cases. So this is confirmed. The control to output transfer function is also confirmed here. Okay. So next step is Okay, so this is the maybe end of lecture 7.